Now we have to review the basic principles behind what we call thermodynamics and kinetics. And we have to understand that there is a difference between the equilibrium of a reaction, which we think of as a thermodynamic process, and the rate of a reaction, which we think of as the kinetics. So kinetics deals with the speed of a reaction or the rate of the reaction. Thermodynamics deals with the equilibrium of a reaction. So we're going to first tackle equilibrium because I think it's a little bit, maybe a little easier to understand equilibrium. So if we have a reaction where, some generic reaction where we have A moles of A plus B moles of B going to C moles of C plus D moles of D, we can write an equilibrium equation for this where we say K, the equilibrium constant, is simply equal to the concentration of C to the little c power times the concentration of D to the little d power divided by the concentration of A to the little a power times the concentration of B to the little b power. So we have essentially the concentration of products divided by the concentration of reactants. And of course to the power of their coefficients, where the coefficient becomes the superscript. It becomes the power that we're going to then you know multiply the concentration by. All right, so in general, in organic chemistry, we're dealing with coefficients of 1, and so we're simply dealing directly with the concentration of products divided by the concentration of reactants, and so it makes it a little bit easier. Now, we say that a reaction is successful if the concentration of the products is greater than the concentration of the reactants. So in that process, if the concentration of products is greater than the concentration of reactants, then K must be greater than 1. And the higher K is, the more successful the reaction becomes. We often will say this: K is greater than 1. I know some students struggle with the greater than and less than symbols. You know, I remember this by the alligator, right? The alligator's eating the bigger amount. So here K is bigger than 1. It's greater than 1. Now, if we recall from thermodynamics of general chemistry, we know that the magnitude of K depends on the Gibbs free energy of the reaction, delta G, right? The Gibbs free energy of the reaction. And we may know that equation, we may remember it. I'm simply going to refresh your memory, where delta G, right, Gibbs free energy, is minus RT times the natural log of K. We've talked about this previously, but you know, I want to get this into your head. Now, understand that R is 8.31 joules per mole K. So, you know, if asked to do a calculation, we certainly need to know that value. Now, oftentimes we confuse delta G, Gibbs free energy, with delta H, enthalpy. And remember that delta H is simply the heat either given off or absorbed in a reaction. And delta G is a little bit more complicated than that. If you recall, delta G is delta H minus T delta S, where delta S is entropy. And so for a reaction to take place, we oftentimes have to think about the entropy of the reaction. Often, delta G has the same sign as delta H, but this isn't always the case. And I'll show you an example in just a little bit of a scenario where that's not the case. So we have to understand some basic terminology. And that basic terminology stems from looking at the energy versus the reaction progress. And so if we start with reactants that have a higher energy than the products do, of course they're going to go through some transition state to get to the product. So that's something that we have to understand. And of course we're going to see that's where kinetics comes in. But the whole process of the Gibbs free energy is looking at the difference in energy between reactants and products. Remember, G and H are what we call state functions, so it's simply looking at the difference between the initial energy and the final energy of the reactants and products. So this is delta G, or oftentimes we think of it as delta H, as in terms of the heat given off. Now, we use delta H often in terms of our terminology, right? So in this particular case, delta G and delta H would be negative because energy is being released. Now, when energy is being released as heat, delta H is negative, and we say that that reaction is exothermic. If delta G is negative, we have another term for that you will see throughout the textbook. And it's a little bit different. Instead of exothermic, it's called exergonic. Okay, so that's referring to delta G. Delta H, negative value, exothermic. Delta G, negative value, exergonic. And likewise, we can take a look at a reaction progress in which the reactants are more stable than the products are, right? So here we have, again, there's going to be a transition state to go from reactants to products. But now you see that the delta G is a positive. I have to add energy to the system to go from my reactants to the products. So delta G, or delta H, is positive here. And we know that when delta H is positive, we call that an endothermic reaction. And again, we're going to have a new terminology. When delta G is positive, it's called an endergonic reaction. So a couple of new terms you may not have heard before: exergonic when delta G is negative, endergonic when delta G is positive. All right? Okay, now let's think about the relationship between delta G and the equilibrium. Remember, delta G is minus RT times the natural log of K. And we've seen this equation before, and we've even seen it rewritten as K, the equilibrium constant, is e to the negative delta G divided by RT. So in general, we can think about a generic case and kind of put things in perspective. When we have a reaction that has a negative delta G, that means it's an exergonic reaction, right? So energy is released. And if we have only a small amount of energy released, something like 1 kilocalorie per mole of reaction of energy released. Remember, a kilocalorie is 1,000 calories, and a calorie is 4.184 joules, and so 1 kilocalorie amounts to 4,184 joules. We have to convert it to joules because R is expressed in joules, right? 8.314 joules per mole K. So when we plug this into the equation, when delta G is minus 4,184 joules, that gives us a K of 5.4. Again, what does this mean, right? We often use equilibrium constants, but we have to really understand what it means. So a K of 5.4, remember, is a ratio. It means 5.4 to 1. 5.4 molar concentration of products divided by 1 molar concentration of reactants. So it's a 5.4 to 1 mole ratio. So if we think about the equilibrium percentage itself, we simply take 5.4 divided by the sum, 5.4 plus 1, which gives us 6.4, and we get an equilibrium percentage of 84.4% of our products. And therefore, we can expect to see a yield of 84% of our products. And that's not too bad of a yield. In organic chemistry, when we get a yield of 84%, we're pretty happy with that. So, so that's something to keep in mind. Now, one thing that we also oftentimes contend with is what we call Le Chatelier's principle. So Le Chatelier's principle states that a system at equilibrium responds to stress in a way that relieves that stress. So oftentimes if our equilibrium isn't highly favored, oftentimes we can apply stress to that equilibrium to get product formation to occur. How do we do that? Well, think about going back to that equation where we set up that the equilibrium constant is the product of the concentration of products divided by the product of the concentration of reactants. Now, the key is to understand that K is a constant. So how would we increase our product concentration? Well, one way that we can do that is we can simply increase the concentration of one of the reactants. Obviously not both of them, but one of the reactants. And when we do so, the equilibrium is going to respond by having to increase the concentration of C and D. So we've only increased the concentration of A. In order for K to remain constant, then that necessitates the concentration of C and D to increase. Hence, we're increasing our product. Now, we're increasing the product relative to B, right? B would then be our limiting reactant. So it's possible that A, oftentimes A might be a solvent. There's a huge excess amount of A. B is our limiting reactant. But we get a lot of C and D because A is in a higher concentration. Another way that we can use this Le Chatelier's principle is by removing products from our reaction. Because if we remove products by either a precipitation reaction or if one of the products is a gas that's evolving and then we can remove it from the reaction itself, then in order for K to remain constant, it's going to drive that reaction to produce more C and D. Because it's losing it, it has to produce more of it relative to A and B so that it maintains its constancy, right? So a couple of ways that organic chemists often use Le Chatelier's principle to maximize product formation. All right? So now that we've talked about equilibrium and thermodynamics, let's start talking about entropy and how entropy kind of can be involved in a reaction. So again, let's recall delta G, Gibbs free energy, is equal to the enthalpy, change in enthalpy, minus temperature times the change in entropy. So delta G is delta H minus T delta S. Now delta H, we can easily calculate delta H. Why? Because delta H is related to the bond energies of reactants and products. So for example, if I have propene and propene reacts with HBr, we've seen this reaction before, right? I get 2-bromopropane. And all I have to do to calculate delta H is recognize the bonds that are broken and the bonds that are made, right? So I see in this reaction, I see bonds that are being broken are the carbon-carbon pi bond, right? It's broken. And the HBr sigma bond is broken. Now, what bonds are being made? Well, I form a carbon bromine bond, and I also form a carbon hydrogen bond, right? Because this is an addition reaction. Hydrogen and bromine are adding across that double bond. So I'm forming new two new sigma bonds, and I'm breaking a sigma bond and a pi bond. Keep in mind, pi bonds are generally weaker than sigma bonds, and we can oftentimes predict that the delta H is going to be negative for this process. So delta H is bonds broken minus bonds made, and therefore we get, so the pi bond is 66 kilojoules per mole, the HBr bond is 88 kilojoules per mole, carbon-bromine bond is 72 kilojoules per mole, and a carbon-hydrogen bond is 105 kilojoules per mole. How do I know this? I can simply look it up in a table, right? So when I look it up in a table, all those values, I can simply sum them up, and I get minus 23 kilojoules per mole of the reaction. Remember, delta G, when delta G, the Gibbs free energy, is negative, it's an exergonic reaction, right? When delta H is negative, it's an exothermic reaction. So this is going to release heat, and in general, delta S is very small, typically speaking, and therefore we can predict that this reaction is going to it's going to release heat, and the equilibrium is going to favor the products. Okay, so understand it's going to release heat, and equilibrium favors the more stable compounds, and in this case it's going to be the products. But how does entropy play a part in this? Well, entropy is related to what we call the freedom of the movement of a molecule, right? So what does that mean? The more ordered a molecule is, the more negative delta S becomes. The more freedom a molecule obtains, the more positive delta S becomes. Now remember, when we're looking at that equation, delta G equals delta H minus T delta S, the more positive delta S is, the greater the entropy, the more disordered a reaction becomes. That means delta S is positive, which means that delta G can become has a potential of becoming negative. Okay, let me show you what I mean by that. Here I have a reaction where I take cyclohexene, and cyclohexene can well, not necessarily spontaneously, but it can decompose into 1,3-butadiene and ethylene. And the way this works is, in essence, you get a rearrangement of bonds, basically. So a sigma bond becomes a pi bond, another sigma bond becomes another pi bond, and a pi bond is actually moved around. So what are we doing in this process? Well, we're creating two new pi bonds. We're breaking, in essence, we're breaking one pi bond, and we're creating three new pi bonds. We're also breaking two sigma bonds in the process. So, but if you look, we're going from one molecule to two molecules. And therefore, this reaction is becoming less ordered. The less molecules that you have, the more ordered a system becomes. The more molecules that you're creating, the less ordered a system becomes. So here we have a less ordered system, more freedom of movement, and therefore the entropy, the change in entropy, is going to be a positive value. So the change in entropy is positive. If we think about the change in enthalpy, well, we have a lot of bonds that are forming that are weaker. We have weaker pi bonds. We're going from one pi bond to three pi bonds, and we're breaking stronger sigma bonds. And therefore, we would expect delta H to be positive in this particular system. So, again, delta G equals delta H minus T delta S. If delta H is positive, in order for the equilibrium to favor product formation, delta G must be negative. If delta H is positive, the only way that we can affect this is looking at that T delta S. Whenever delta S is positive, then we have that temperature function. And you notice as we increase temperature, then that term minus T delta S is going to increase. So in order for delta G to be negative, we have to increase temperature. And this is a scenario in which when you know that delta S is positive, you can always get the equilibrium to be favored toward the product if you increase temperature. Because eventually you're going to reach a state where that minus T delta S is a greater value than delta H, and therefore delta G becomes a negative value. Okay? So now let's take a look at how kinetics plays a part in a reaction. Okay, so one thing to understand is that just because a reaction is thermodynamically favored, when we say that delta G is exergonic, right? It's a negative value. That does not necessarily mean that it proceeds at an appreciable rate, right? So something that might be thermodynamically favored can still be very slow. Why is this? Well, when we plot energy versus reaction progress, remember we had reactants and we had products. And so let's assume we have this exergonic reaction, right, where we have delta G is a negative value because energy is being released. But remember that we had this activation energy, right, a transition state to go from the reactants to the products. In other words, we're going to have to supply energy to go from the reactants to the products. And that energy is oftentimes referred to as a barrier, the energy barrier. And this energy barrier has to be surmounted in order for product to actually form. We call this the activation energy. And there are a number of terms that are often used, but oftentimes you'll see the activation energy being expressed as a delta G with a dagger, a double dagger, delta G double dagger, right? This is referred to as the activation energy. Sometimes you'll see it as EA, activation energy. This particular textbook uses delta G dagger, okay? So it means the same thing, and that is the energy barrier that needs to be overcome in order for a reaction to occur. Now, how do we overcome that energy barrier? Well, molecules exist in a distribution of energy states, which we call a Boltzmann distribution. So if we plot kinetic energy versus the number of molecules with a particular kinetic energy, we see that we get this Boltzmann distribution. So what does that mean? That means that the average energy of molecules is somewhere, at the peak, but there are some molecules that have very high energy and some molecules that have very low energy. Now let's say that we needed, we have a reaction, and in order for a reaction to take place, we have this barrier, this activation energy. And if we're looking at a Boltzmann distribution of molecules, well, we see that there's actually very few molecules that have enough energy to actually overcome that activation energy. Well, how, is there a way to affect this? There certainly is. Remember that kinetic energy is related to temperature. So going back to general chemistry, we see that kinetic energy is 3/2 RT. And so kinetic energy is directly proportional to temperature. As we increase temperature, we increase the kinetic energy of molecules. So our distribution changes and it looks something like this. And now you see that there are many more molecules that have enough kinetic energy to overcome that activation energy. So at higher temperatures, more molecules have enough energy to overcome that barrier. And oftentimes, kinetics is related to temperature. Kinetics is related to temperature. If we have a slow reaction, we can get it to speed up by increasing the temperature, which increases the kinetic energy of the molecules, and therefore there are more molecules that have enough energy to overcome that activation barrier. Okay? Now the rate of a reaction, right, the kinetics also depends on the concentration of reactants. So it depends on the temperature we see, but it also depends on the concentration of reactants. And we have, and like I said, we're going to focus on two types of reactants here, even though it's a substitution reaction. The first one is called a first order kinetic reaction, and this is when the rate depends only on one reactant. When the rate of the reaction depends only on one reactant. So for an example, I have tert-butyl bromide and it reacts with water. Water is the nucleophile, tert-butyl bromide is the electrophile. It's the Lewis acid. And it undergoes a substitution reaction and produces tert-butyl alcohol plus H, that should be HBr, not HI, HBr. So when I run this reaction, I typically run this in water, right? You basically take tert-butyl bromide and you run the reaction in water, and you observe that the rate simply depends on K, which is a constant, times the concentration of tert-butyl bromide. Notice water as a reactant isn't part of the rate. Water has no effect on the rate of the reaction. So when you have a rate only being determined by the concentration of one of the reactants, this is called an SN1 reaction. SN1, why? Because it's a substitution, S. It's a nucleophilic substitution, so that's where the capital N comes from. And the 1 means that it's unimolecular. Unimolecular. 1. What? What does unimolecular mean? That it means that the rate depends only on one molecule. And in this particular case, it depends on the concentration of the alkyl halide, right? Then we have a second order reaction, kinetic reaction, which is when the rate depends on two reactants. And obviously if we had more than two reactions, we could get a third order and a fourth order, but you know, for our purposes, we're going to focus on first order and second order. So here I have an example where I have 1-bromobutane reacting with hydroxide. Hydroxide's a Lewis base, right? The nucleophile. The electrophile is the alkyl halide. I undergo a substitution reaction, and now I get 1-butanol plus bromide. And when we study the kinetics of this reaction, we see that the rate of the reaction depends on the concentration of 1-bromobutane, and also it depends on the concentration of the hydroxide ion. So as if we doubled the concentration of the alkyl halide, we would double the rate. If we double the concentration of hydroxide, we would double the rate. Also notice I say K primed, right? So K is a constant. Now, rate is concentration per time. Obviously, when you go from a first order to a second order, in order for the rate to have the same units of concentration per time, K, that constant, has to have different units. So your textbook goes into detail about that. You're never going to be asked to calculate K, but it's certainly an interesting component to understand that K for a first order and K prime for a second order have different units to them. Now, when you have a rate that depends on the concentration of two reactants, it's called an SN2 reaction. SN2. Why? It's a substitution reaction. It's still, a nucleophiles reacting with the alkyl halide, but this time it's what we call bimolecular. Bimolecular, which simply means that the rate depends on two molecules instead of one. So here the rate depends on the alkyl halide and it depends on the nucleophile. Okay? All right, that's a lot to kind of wrap your head around the difference between thermodynamics, equilibrium, and kinetics, the rate of the reaction. So let's try to summarize what I've just talked about and understand the key concepts. One of those key concepts is that even a thermodynamically favored reaction can be slow if the activation energy is high. And let me show you an example of this, of combustion. So we know that combustion is very thermodynamically favored. We talk about the delta H, and all of this energy is given off, right? So I can look at a simple equation where I take methane and I react it with 2 moles of oxygen to produce carbon dioxide and 2 moles of water. The delta G for this reaction is huge. It's 801 kilojoules of energy is released per mole of methane burned. Now, if we think about this just from the standpoint of organic chemistry, and we think about all of the organic compounds, namely, we are made of organic compounds, we see, well, gosh, if we were to combust, there'd be a lot of energy happening. So one question that you might ask yourself is, well, why don't we spontaneously combust? And the answer deals with kinetics. Taking this simple reaction, we see that methane and oxygen are the reactants, and CO2 and water are the products. And there's certainly a huge delta G there, but there also happens to be a huge activation energy. And it's that activation energy that stops these methane from spontaneously reacting with oxygen. So when you have a high activation energy, you need to have a spark of energy to start the reaction. Now notice when I spark methane and oxygen, literally, right? I give it energy to overcome that barrier, that activation energy. And now energy is being released, and oftentimes that energy is released can fuel the activation energy. It can go back into the reaction to give the reactants enough energy to overcome that activation energy barrier. So oftentimes you need a spark, and then the reaction can continue. But this is why we don't spontaneously combust, which is kind of cool. And understanding the relationship between thermodynamics, equilibrium, and kinetics is important in understanding the mechanism of reactions.